Hello and welcome to lecture 22. In last lecture we were solving a numerical, that's what was to calculate what is the variation of my flow angle by considering free vortex configuration and by considering say constant reaction configuration. Now today let's take one more numerical, that's what will be based on the free vortex and exponential kind of swirl distribution. So that's what will be giving you some other kind of feeling in sense of understanding the methods or design concept what all we have discussed in past few lectures. So we have our axial flow compressor with total pressure ratio of 1.02 and it is operating at 6000 rpm. The estimated stage isentropic efficiency and work done are 92% and 0.98 respectively. The hub and tip radius are 0.18 meter and 0.25 meter respectively. Consider the ambient conditions at the entry as P01 equal to 101325 Pascal and T01 as 288 Kelvin respectively. Calculate the variation of degree of reaction and axial velocity using free vortex swirl distribution and exponential swirl distribution. It says take axial velocity and degree of reaction as 30 meter per second and 0.65 at the mid station. So here in this case it says we are looking for calculation what is happening with our degree of reaction and what is happening with the change of axial velocity. That means we need to have some understanding of these methods. So let's see how do we proceed with. It says we can have this data, so pressure, temperature, pressure ratio, my tip radius, hub radius, rotational speed, efficiency and blockage factor, they are known to us. We would like to calculate the degree of reaction. So in order to have your degree of reaction to be known, we need to have the calculation of whirl velocity component. Okay. Now when I say we are looking for whirl velocity component, we need to go with arbitrary distributed whirl velocity distribution at the entry and at the exit. Okay. So let's move it. So what we know is we are looking for say delta T0 for calculation in a later stage. We are looking for say degree of reaction, that's what need to be calculated at mid station. Okay. So if we write down, we have our temperature ratio, that's what is given by 1 plus pi c to the power gamma minus 1 over gamma minus 1 divided by efficiency. If you look at our pressure ratio is known to us, efficiency is also known to us, that's what will be giving me my temperature ratio as 1.0061. Since this is what is low speed compressor, you can say my pressure ratio that is also say lower, it is 1.02, that's what will be giving me my temperature ratio in this range. We know what is our entry temperature, so based on the temperature ratio we can calculate what will be my outlet temperature. Now once the outlet temperature is known to me, we can calculate what is total temperature rise in the stage, that's what we are writing as delta T0, it is 1.77 Kelvin. Okay. Now at this moment we are not having idea how the whirl velocity component it is been distributed. So we can safely assume say generalized constant work distribution, we can say CW1, that's what is A into r to the power n minus b by r. That's what we are considering at the entry or at the rotor inlet. My Cw2 we can say A into r to the power n plus b by r at exit. Okay. Now, in order to simplify this solution, let me introduce one non-dimensional parameter, say capital R. That is nothing but my radius or my location at particular station divided by my mean radius. So, if this is what is your case, in place of R in this equation, what we have assumed as Cw1 and Cw2, I can replace that with say Rm into R. So, if I will be putting this formula, it says my world component distribution that can be written as capital A into capital R to the power n plus or minus b by r. Okay. So, where we are putting our constant as a small a into Rm to the power n and b, that is nothing but b by Rm. Now, from our vortex energy equation, so this is what is my vortex energy equation, what we have written. Since we have modified our equation in terms of capital R, so in place of writing small r, I can put my capital R, and if I am simplifying this equation, this is what is the formulation for say my distribution of axial velocity or variation of axial velocity with radius and variation of my world velocity component with the radius. So, this is the equation which we will be using for calculation of variation of axial velocity for both the methods. Now, let us take first method. What it says? It says free vortex distribution. So, when I say free vortex, we can say my exponent n we are putting as minus 1. So, let me put n equal to minus 1. So, my Cw formula, that is what will be changed to A by R plus or minus B by R. So, you can say we can safely write down my Cw1, it is A by R minus B by R, and Cw2, that is A by R plus B by R. So, now we know what is our world component at the entry and what is our world component at the exit. Now, what we learned, we are having our axial velocity variation, that is what we have derived with simplified vortex energy equation. So, in this equation, in place of Cw, we can write down it is A by R plus or minus B by R. If we are putting this in this formula, we will be getting say 1 by 2 dCA square by dr equal to 0. If that is what is your case, you can say my axial velocity is constant. So, we can say for free vortex, we have also seen say this is what is our required condition. We need to have satisfaction of 3 conditions. One, that is what is say constant total enthalpy. Second, that is what is my constant axial velocity, and third, that is what is Cw into R equal to constant. Okay. So, that is what it says my axial velocity is coming to be constant, and that is what will remain 30 meter per second at the entry of my rotor as well as at the exit of my rotor. Now, next, that is what is to calculate your degree of reaction. So, degree of reaction, that is what we can rewrite down as 1 minus Cw2 plus Cw1 divided by 2u. In this equation, we can write down my Cw1 and Cw2, that is what is A by R minus B by R, and second, that is what is A by R plus B by R. So, if we are putting this together, it says my degree of reaction, it is nothing but 1 minus A by UR. Now, what we have assumed, we have taken our capital R as R by Rm. So, we can write down my peripheral speed at particular station, that is what we can write down U equal to U mean into capital R. Okay. So, this is what is your case. You can write down my degree of reaction, that is what is given by 1 minus A divided by Um into R square. Okay. Now, what we know for our case, at the mid station, so we can say R by Rm, so Rm by Rm, that's what will be getting cancelled. So at mid station we can write down it is given by 1 minus A by Um. So you can calculate what will be the constant A. So for that we are looking for U mean. So U mean we are writing as omega into Rm. Since my hub diameter, hub radius is given, my tip radius is given, I can calculate what will be my mean radius. So this is what is my mean radius, and omega we already have calculated based on 2 pi n by 60. It is 628.32 radians per second. So we will get our mean peripheral speed as 135 meter per second. Okay. Since my is known to me, I can calculate what will be my constant A. So my constant, that's what is coming, 47.25. This is what is my capital A. Now what we know from our fundamental understanding of energy balance, my aerodynamic work and thermodynamic work, they both will be same. So if we are putting in this form, it says my B will be coming in sense of delta T0. So you can say B, that is given by Cp into delta T0 divided by 2 lambda into Um. Now we already have calculated our delta T0, it is 1.77. Cp I can write down 1.005 into 10 to the power 3 divided by 2. Lambda is known to us, that's what is 0.98, and this is what is 135. So that's what is giving me what is my constant B, and that is coming 6.72. Okay. So based on this we can calculate what is our constant A and B. Now what is our target? We are looking for calculation of our degree of reaction. So for that purpose we can write down here, in this case my Cw1 plus Cw2, that's what is given by 2A divided by R, and we can write down Cw2 minus Cw1, that's what is given by 2B divided by R. So at hub, this is what it says, it is given at this station, it is 0.387. We can have this RH, it is 0.837. So we can put this equation, it says this is what will be giving me what will be the variation of my whirl component at the entry and exit at the hub. Okay. So this is what will be giving me how my whirl velocity component, that's what is varying at the entry and exit. Now in line to that we can do our calculation at the mean section. In line to that we can do our calculation at the tip section. So we can say our swirl velocity component at the mid station, it is coming 53.97 meter per second, and at the entry it is 40.53 meter per second. Same way we can do our calculation at the tip, that's what is coming, say 46.52, and at the entry it is 34.94. Now based on this understanding we can calculate our degree of reaction, that's what we have derived as 1 minus A divided by into R square. Okay. So different R value we can put. Suppose if I will be putting at say mid station, that's what is because capital R is 1. At hub we can calculate, because my ratio of R by Rm you can calculate, that's what is coming 0.83. Okay. This is giving me my degree of reaction at the hub as 0.49. At tip we are getting our degree of reaction to be 0.73. So this is what is all calculation when we are considering our free vortex configuration, in which our axial velocity, that's what is constant, and my degree of reaction, that's what is varying from 0.49 at the hub to 0.73 at the tip. Now what next is asked to us, it is to consider exponential swirl velocity distribution. So if that's what we are considering, we say my n, that's what is equal to 0. So in equation, if I will be writing my n equal to 0, it says my CW1 that is given by A minus B by R, and my CW2 that's what is given by A plus B by R. So at the entry we are considering A minus B by R, and at the exit of my rotor it is A plus B by R. So these are the two wall components, that's what we have come up with. Now based on our vortex energy equation, if we will be putting this equation where my CW I am writing as say A minus B by R. So if we are putting this together at the entry, what it says, at entry we can say A minus B by R. So this is what will be giving me the variation of axial velocity. So you can understand this is what is not coming to be 0. That means we need to literally calculate what will be the variation of axial velocity for a particular station. So for the sake of simplicity, what we are putting, we are considering mean radius. We know that's what is R by Rm is say 1. So this I am putting as one limit, and arbitrary radius I say it's R. So putting my limit and putting for integration, say R equal to 1 to R, integrating this equation and this formula, when we are simplifying this term, my axial velocity at the entry, that's what we are getting as CA1 square equal to CA1 at mean station square minus 2 A square natural log R plus AB 1 over R minus 1. Now here in this case, just remember CA1m is nothing but my axial velocity at the mean radius, and CA1 is nothing but my axial velocity at particular station. So in line to that, if you will try to solve the equation by putting say A plus B by R, you can get my CA2. Okay, that is nothing but my axial velocity at the exit of my rotor. That's what will be coming in this formula. So it says my axial velocity is varying at entry, my axial velocity is varying at the exit. It is not remaining constant. Okay. So if we are looking for calculating our degree of reaction, so this is what will be the formula. If you are simplifying all these things together, that's what will be giving me my CA square minus CA1 square minus CA2 square equal to 4AB into bracket 1 minus 1 by R. Okay. Now here in this case, what all we know, we are putting our degree of reactions. Since we know what is our CW1, CW2, we have our equation in the formation of CW2 minus CW1, that's what is correlating. Just remember that's what is correlating my B, and this plus that's what is correlating my A. So A and B, that's what is a constant. So this is what we have already seen in our past calculation. So we will not be repeating the same thing. So if we are putting this together, my degree of reaction, that's what is coming as 1 plus A by UM into bracket 1 minus 2 by R. Okay. Now we want to calculate what is our constant A. So constant A we are writing as say UM into 1 minus degree of reaction at the mid station. Since we already know my degree of reaction at mid station, that's given 0.65. If I am putting into this equation, that's what will be giving me my constant A, and that is 47.25. Same way we can calculate our B, that B is nothing but that's what is based on our energy balance. Say my thermodynamic work and aerodynamic work both are same. Based on that we can say my B is Cp delta T0 divided by 2 lambda into UM. That's what is giving me B as 6.72. Okay. Now once we have calculated this constants, we can calculate what will be my CW1 at the entry and at the exit at 3 different stations, at hub, mean and tip station. So this is what is a formulation, that's what we have already discussed earlier. So at hub we can say we are getting 55.27 meter per second. At the entry, we are getting our work component as 39.22 meter per second. For mid station at the exit, we are getting that as a 53.97 meter per second, and at the entry we are getting 40.53 meter per second. In line to that, at the tip also we can calculate. It says my CW2 at the tip it is 53.04, and at the tip at the entry we can say it is 41.46 meter per second. So because of repetitive stage, we are not showing all calculations here. Maybe you can do pen paper work and you can get with this number and verify these numbers. Now we are looking for what is happening with our axial velocity. So if you recall, we have derived CA1, that is nothing but my axial velocity at the entry. That's what we have correlated in sense of our axial velocity at the mid station and constant A, B and R. R is nothing but it is at particular location. So if I am looking for my axial velocity at the entry near the hub, I will be putting these numbers. It says my CA1 at the mid station is 30 meter per second. This A we have calculated, it is 47.25. B we have calculated as a 6.72, and R we have already calculated for hub. It is nothing but RH by RM, it is 0.837. Okay, and that's what will be giving me my axial velocity at the entry near the hub. Similarly, we can calculate our axial velocity at the entry near the tip region. It is coming 18.02. Just imagine, at the mid station we are having our axial velocity to be 30 meter per second. Okay, and at the hub we are having 39.63. Near the tip, that's what is 18.02 meter per second. So it's a great variation of my axial velocity. Similarly, we can do our calculation at the exit. So if we are putting our exit at the mid station, we have our axial velocity as 30 meter per second, and this constant A and B we can put. That's what is giving me my axial velocity at the exit near the hub is 42.63. Just look at these numbers. This is what is showing some great variation compared to our 30 meter per second at the mid station. Same way at the tip station we can calculate, that's what is coming 12.23 meter per second. Okay, so this is what is the indication when we are considering our exponential design. We are having say variation of our axial velocity at the entry and our variation of axial velocity at the exit of my rotor. Now if we are looking for calculation of degree of reaction, we can say that's what is given by 1 plus A divided by um into bracket 1 minus 2 by r. This is what we have derived. Okay, so whenever you are taking any exponent, maybe you can come up with some other exponent. Make a habit of deriving this thing. That's what will be helping you in order to calculate what all parameters, that's what is going to change. Mainly degree of reaction, my axial velocity, they are of great interest at the initial stage of design. So if we consider my degree of reaction at the hub, that's what is coming 0.51. If we consider at the mid station, that's what is given 0.65, and at the tip, that's what is coming 0.74. So this is what is giving you idea how my degree of reaction, that's what is changing when we are considering our exponential world distribution. So let's have comparison of these two. So if you are looking at, say, this is what is representing along the span how axial velocity it is varying. When we are considering we are having free vortex design, my axial velocity is 30 meter per second, and that's what is constant throughout the span. Now here in this case, if we are considering say exponential method, we are having variation of axial velocity at the entry as well as at the exit. So if you look at, this is what is representing the variation of axial velocity at the entry. So you can see from hub to mid section, my axial velocity, that's what is going to decrease, and on later stage from say mid section to tip, my axial velocity is going to increase. But at the same time for the exit, if you look at, I am having larger velocity near the hub, that's what is going to decrease here. In line to that, near the tip region, our axial velocity at the exit is coming to be lower. Okay. And if we try to compare the degree of reaction, we can have look at these numbers. If we look at, there is not much variation in sense of degree of reaction. That's what is happening both near hub and tip region. So we can say this is what is giving some different kind of feeling. Now let's see what is happening in sense of my world distribution. So here if you look at, this is what is representing the comparison of free vortex and exponential loading at tip, mean and hub station. So if you compare my delta CW for both the methods, they are coming same. Okay, they are coming same. If you are looking at the entry CW1, exit CW1, entry CW1 and exit CW1 for both the methods, at the mid station they are same. But when we are comparing near the hub region, you can say we are having say great reduction for exponential method. Okay, and when we are comparing near the tip region, my world component is coming to be higher. So this is what all is giving us idea what all we need to do in sense of systematic calculation. So by solving this numerical, we are initiating some design idea to build the confidence that you can do your design based on what all approaches are given to you. And at the same time, this is also giving you hint what all parameters they are getting changed when I am assuming particular design. So free vortex design, that's what we discuss as, that's what is giving highly twisted blade. When we are looking at constant reaction design, we have discussed that's what is not satisfying your radial equilibrium. When you are going with say exponential method, again you will be having variation of axial velocity. We have discussed about our fundamental methods also, where we are neglecting our radial equilibrium. So with this we are stopping with. Thank you very much. See you in the next class.